All right, we have a couple more things to cover here, but then this chapter's done. Yee-hoo! I just want to kind of like go back and like do a little alpha thing with you guys. So imagine we have krypton. So you get your periodic table out and you look for krypton and figure out it's got 36 electrons. So where do those 36 electrons go? Where do I put them and how do they go in? All right. So first one's going to go into the 1s, right? It's the lowest energy. That's where they all want to go. So first one goes in up. Second one goes in down. Next available spot is 2s. So that one goes in up. Then one goes in down. When I get to the 2p, when these guys fill, they fill one at a time. Spin up. Then they start pairing up. Spin down. All right. Next two are going to go up here in the 3s. Then we have 3p. Remember, they fill one at a time. Then they go upside down. Yeehaw. Then the 4s is going to fill. One up, one down. Now it's all full. 3d. All right. It's degenerate set. So one at a time. All 5 of them. And then pair them up. Boom, 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 boom. And then last 4p. Boom, boom. Those 4. And there we go. There's all 36 electrons. All right, when all of the electrons of your atom are in the lowest possible orbitals, energy states here, orbitals, that is what we call the ground state, right? It's the lowest energy state that it could be in. Now, if I take any one of these electrons, if I were to take one of these 4p's and then put it up into like a 5s or anything, just any other higher energy orbital, that is what we call an excited state. I can take one of these 2p's and move it way out there, and like that would be an excited state. So there's all sorts of different excited states, but there's only one ground state, and the ground state is where all of your stuff is in the lowest possible arrangement that it could be in. All right, cruising along. Like those orbital diagrams are cool, but you can imagine it would get kind of unruly to do a big one, like with lots and lots of electrons and drawing all sorts of boxes and arrows and this, that, and the other thing. So there's kind of a shorthand that we can do, and we call those electron configurations. And it's a whole string of like number, letter, number things that you're going to see here. All right. So it's going to show where all the electrons are, just like this does, but it's going to be just a slightly more user-friendly manner to it. So each one of these little chunks is going to have a number that tells me the letter, so 4. There's going to be a letter denoting the type of orbital, so either S, P, D, or F. And then the superscripted number tells you how many electrons are there. All right, so let's do an example of what I'm talking about. I'm not going to do all of these. I figured I would do sulfur, and the other ones we can fiddle around with in person or on Zoom or whatever we happen to be doing at the time. So let's just do sulfur and get the electron configuration for sulfur. So first thing I would do usually is I would find, here we go, a periodic table, and I'd find sulfur. So what I'm going to do, and what I'd normally do, is I'd stick my finger actually on sulfur. So I'd be holding the piece of paper down, my finger right there, and I want to fill all the way up until I hit sulfur, because sulfur has 16 electrons, and I know that because it's atomic number 16. Right, so I'm going to put 16 electrons in. Where do they go? Well, they start off in the 1s, then that fills, then it goes 2s, right? So this is the 4th box over. So I'm going to flip to this thing. So the 4th box over. So if I'm holding my finger there, I'm going to fill up the 1s, the 2s, the 2p, the 3s, and then when I get to the 3p, there's only 1, 2, 3, 4 electrons in that one. So what does that look like on here? Go through real quick. Bop, 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 bop. And last one, boom. So the way I'd write the electron configuration is it'd be 1s2, 2s2, 2p6, 3s2, 3p4. All right. And this is going to seem kind of crazy at first because like, oh my gosh, that looks like some kind of evil code. It really is easy. And I would suggest like do every element all the way up to krypton. And by the time you get to krypton, you're going to get that pattern. It's going to be really easy. And you'll be able to do it in your sleep after that. There is a shorthand, all right, because some of these will get really crazy. What we can do is we can go to the previous noble gas. So what do I mean by the previous noble gas? Well, sulfur is atomic number 16. So the noble gas that comes before that, boop, is up here. That's neon. All right, that's got 10 electrons. So when I go back here, this is basically the electron configuration of neon, right? These first 10 electrons, the 1s2, 2s2, 2p6, those 10 electrons, that's neon. So I can write neon 3s2, 3p4. And that's the same thing. That'll be really nice, especially if you're doing electron configurations of like barium or something, because that gets humongous. All right, a couple more things here. Making good time. All right, there are a few goofy, oddball configurations that aren't what you would normally predict, and you just have to memorize them. All right, so the ones you guys need to know are chromium and copper. So normally when I do chromium, you'd say, okay, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. All right, and that's wrong. There's something weird that happens, like there's a special stabilization you get when you have exactly filled, like totally filled shells, or perfectly half-filled shells. That is the theory on it, that you get this extra stabilization when these sublevels are either perfectly completely filled or they're exactly halfway filled. So when I had 4s2, 3d4, remember, like, how many electrons can actually go into the d sublevel? Remember, there's 5 different d orbitals, right? It holds a grand total of 10. All right, so it's almost halfway. It's got 4 in there. So what ends up happening is that one of the electrons comes out of the 4s and goes into the 3d. So it ends up being 4s1, 3d5. So both of those things exactly half filled. And kind of a similar thing happens with copper, where instead of being argon 4s2, 3d9, as you would predict from the stuff I just told you, it's going to be argon and 4s1, 3d10. All right. So those are the 2 little goofballs. You're just going to have to memorize those. Last thing, woohoo, Lewis dot representations. So we're going to start doing Lewis dot structures a few chapters from now, but this is planting the seed in your brain as to what a Lewis representation is. And so a Lewis dot representation uses dots to represent our valence electrons. So remember, the valence electrons are the outermost electrons. So we have core electrons on the inside, and then the outside, those highest energy electrons, are the ones we call the valence electrons, the ones with the highest principal quantum number. That's the other way we can talk about it. So the highest n value. All right. So you put dots around your symbol. So if I had just one valence electron, I just put 1 dot around my symbol. So we use the top, the bottom, and the left and the right as our places. So you kind of think of it as having only 4 slots to put electrons into, and we put them in one at a time. So if I have 1 dot, I just pick a side and I put a dot on it. That's fine. If I have 2 dots, normally they don't put them together. They don't like to pair them up until they have to. So I'll just pick 2 different sides and put 1 dot on each side. Usually most people will put them on opposite sides. So if I only had 2 dots, I'd put 1 on top, 1 on bottom, or 1 on left and 1 on right. 3 dots, just pick 3 different sides and put 3 dots around your symbol. 4 dots, obviously put 1 dot top, 1 dot bottom, 1 dot left, 1 dot right. And then when you get the 5, just whichever one you pair up, that doesn't matter. And we'll go over more of these in class, but it's easy. What you don't want to do is put more than 2 dots on one side. So you don't want to have like oxygen with like a whole bunch of dots, like 6 dots on the side of it or something weird. And you don't want any more than 8 dots total around the symbol. All right, we'll get to the reason for that once we get to the periodic table. It's the octet rule. Yeehaw! But that is it. You made it to the end of chapter 5. Chapter 5 is a monster chapter. There's a lot of like mind-crushing stuff in here. But go back, watch these things, read the textbook, ask me questions, and it will start to make sense. All right, see you in the next chapter.